strategic partnerships that in the digital sector at the National Physical Laboratory, where the focus is on delivering confidence in the intelligent and effective use of data. Andre's led to the creation of NPL's Assured Autonomy programme, which brings together disciplines across data science, time and frequency, electromagnetic technologies, and dimensional metrology. His work on autonomous transport systems is focused on building collaborations across the UK's transport sector, so land, sea, and air, to establish an integrated digital measurement infrastructure and technical framework to underpin simulated testing ecosystems for autonomous systems at all technology readiness levels. Okay, so there we are. That's Andre. And Andre, you're going to tell us a little bit more about NPL for people who aren't familiar with NPL, which has been going for a long time now. I'm not sure when it was established, but certainly all of my lifetime at least.
Yes, it's been going for quite some time, since the beginning of the last century, actually. It is obviously the UK's National Measurement Institute. It is a world-leading centre of excellence in developing and applying the most accurate measurement standards and science and technology available. I think we have about, I may be correct on this, about 850 scientific experts operating in over 300 laboratories. And we're centred in Teddington, but we do have facilities across the country increasingly. And we really use our measurement science and the technology to have a positive impact in the real world. And we deliver solutions critical to supporting business success, both in the UK and elsewhere. This includes things like resilient timing, infrastructure, advanced underwater acoustics, unhackable quantum communications, and superfast 5G. And in all these instances, if you like, these advances must be built on a foundation of reliable measurement and confidence in that data to succeed. So that's very much what we do. And I'll start with my presentation, therefore. I've actually managed to bypass one of those slides just by talking about NPL. So if you bear with me 1 second while I get this live.
Okay, so I'll give people the title meantime. So the title is an assurance framework for maritime autonomous systems, as you can see. And thank you, Andre. On you go.
Right, can everyone see the slide? Yep.
Yeah.
Good, fantastic. That's always one of the key things I need to get through, first of all. Basically, I've been introduced, so I don't need to go into that bit. But the topic today is the assurance of maritime autonomous systems. Now, the premise of this talk is that, and it's a very simple premise if you like, but ensuring confidence in the safety, reliability and performance of emerging maritime autonomous systems is going to be key to the speed at which they're exploited and the benefits of them can be derived. So that's perhaps a bit obvious, but to achieve this, however, it does present a whole new set of challenges, and the solutions to which are sometimes yet to be invented or else even proven to work. Now, although the presentation focuses on maritime autonomy as the case study, there is increasing evidence that the same or similar challenges can be evidenced and solutions developed across all connected and autonomous mobility. Moving on to about NPL, I've already just introduced NPL, so I'll move on to the next slide about that. And this is really to stress the fact that we are moving into this digitally transformed world. And in this, governments, individuals and organisations are increasingly relying on data and decisions which have been sourced from, or some would even say outsourced to, emergent technologies. Now, confidence in these systems is vital, and without the means to consistently measure the quality of data, it will become hard to reliably quantify the risk associated with decisions which are derived from that very same data. And some of the issues, I'm sure many of you will have heard of these before. There's the garbage in, garbage out. So in other words, whatever you put into a system will affect the quality of the outputs. And in that, we face a shortage of generally accepted and understood standards of quality, for example, around calibration, timeliness, incompleteness. It's also understood, or rather, is it understood, what has been done to the data between it being gathered and it being actioned upon. And then there's always the conundrum around black boxes, and this does confound regulators quite heavily, particularly how to explain machine learning and understand where the risk of bias is present. So our focus is on how we use our measurement science to provide confidence within and throughout systems. And confidence really in this requires an understanding of how good the measurement that created the data was. Also understanding enough about the measurement conditions to know the data is suitable for the intended application, and also the effects of any processing to be done to the data. So you'll see here we follow this model of collect, connect, comprehend to try and keep this as simple as possible. But it's really not that simple. But all the way through this, we're looking at how you apply the right type of measurement to this. And key aspects of this are indeed uncertainty quantification and propagation, the data provenance and metadata associated with that, and also looking at trusted algorithms and software as well. So you might recognize this statement, but I get asked many times, what's our definition of autonomous systems? From the context of of how we can use this on a consistent basis, and for the purpose of what we're doing in maritime autonomy, we've sort of settled on this approach, but I know there are many other definitions as well that could be used. You'll notice it's actually been derived from the EPSRC definition of trustworthy autonomous systems. So there are other descriptions of autonomy, but I think this one does sit well, and not least because I think it also brings in the human element very heavily on this. But it also, I think you can see instantly through this that there are a number of questions being raised, including legal and ethical ones, and ones which we've actually encountered when we're looking at autonomous transport or mobility. So, for example, one is, when does a system go from being one which uses automation to assist a human to one which makes decisions and thereby takes control on behalf of the human? And can we actually understand and define where responsibility lies along that spectrum? And this is becoming an increasing issue, and it is something which is a paramount issue in the maritime space, because, as you'll see, there's often a sort of an increment of going from systems which are assisting decisions to ones where people just hand over that decision making, normally because a number of systems have come together and people suddenly don't realise they're actually in something that's piloting itself and making those decisions. And this is a very important area that needs to be addressed. So why does it all matter? Well, understanding the need for assurance is important, as we said, because confidence in the safe and reliable operations is paramount, and particularly if businesses or consumers are going to use them, we're going to rely on these systems, but also those who are investing in these businesses and those who are going to insure them, etc. Now, these quotes here are just really an indication and mainly highlight things like the safety and economic impact of bad design and assurance approaches. So it's not always, by the way, that say an autonomous system itself is bad. It's just been assured badly, or it's not been understood what use it should be applied for, particularly in the case of the 737 MAX. But it does also point for the need for quite a myriad of different activities and elements to come together to assure a system. But it also emphasises, I think, that really how it's important to understand how humans understand and interact with these systems. I think this goes to the core of what people have been looking at when they talk about trustworthiness as well. So there's this element of assurance, but also this element of reassurance in this as well. Another thing I'd also say, though, is I think the media has tended to focus when things go wrong with autonomous or automated systems, rather than describing the future benefits of these systems. And I'd also say, observationally, that it would appear, certainly in places like the UK, there's a growing number of seemingly well-designed and potentially viable systems, certainly going through trials. But one of the big challenges, and this is where we've been in discussion with the regulators as well as industry, is one of the key missing areas, and which really is this barrier to adoption, is how to consistently and independently demonstrate, and in a way that is easy to understand, the reliability, safety, and performance of such systems. And that in particular, it's understanding these systems which have been designed to operate outside of or with only limited human supervision. So in terms of what MPL has been focusing on, increasingly over the last 4 years, been focusing where we can best apply our measurement capability to support the UK's development and exploitation of autonomous systems. And this does include the transport sector, and the transport sector has been a major area of focus. That's not least because government and industry is investing a lot into that. It is a particularly exceptional set of safety and reliability challenges inherent in it, but also the benefits are quite considerable if they can be realised. And so we've taken a particular interest, but not a sole interest, in this principle that you cannot divorce the quality of the inputs, for example, from perception systems to the decision making, from how you actually test the decision making system itself. Now, this presents a significant data quality and system assurance challenge, and our focus has been, certainly at least currently, is on the following sort of areas. So the insufficiency of the existing functional testing and the requirement for new testing and measurement approaches. Also, that current simulation environments cannot yet provide a reliable link to real-world testing. It doesn't mean it's not possible, but currently they don't. Also, how to examine and validate machine learning and AI systems, and also the requirement for robust data quality standards. Additionally, the importance of quality infrastructure, including communications and traceable time signals, are very important and should not be underestimated either in this. So before I get on to talking specifically maritime autonomy, our work has been very much driven by collaboration, driven by stakeholder engagement, goes to the heart of the work we do. And I think it's also a reflection partly that no single organisation is ever going to crack this, and certainly I don't think MPL thinks that at all. We do see, though, that very good solutions are evident where there's very good collaboration. The work we've done to date so far is a result of a multi-year collaboration, investigation with stakeholders across the transport sector and more widely, including the sort of leading maritime organisations and government agencies and academia in this. So what we're going to now look at is the specifics, how we are applying this thinking into the assurance of MAS, or maritime autonomy, autonomous surface ships, or maritime autonomous systems, depending on how you want to describe them. There's a lot of different acronyms out there. So it's a growing view in industry, and this is reflected in government figures, which you can see here at the top, that maritime autonomy is a disruptive technology that will, over time, come to replace more traditional alternatives, but most specifically in areas where human endurance, cost, availability, and safety are limiting factors. So it's not going to replace humans through and through at all. I don't think people generally feel that or see that happening, but there are areas which are underexploited where certainly we're going to see more of that. Some of these are described here. Certainly things like offshore renewables and aquaculture are areas where it's pretty evident already, and there's a lot of good research on this, where there would be significant cost savings through the greater deployment of autonomy, but also actually the acceleration of the deployment of these renewables and other aquaculture technologies as well. And that's also related to environmental monitoring, which is a very important area for the oceans and the seas. But also the development of new opportunities in trade and also around decarbonisation, particularly things like short sea shipping, or better management of vessels, or reduction in their overall tonnage, etc. There's quite a few opportunities, but it's not everything is going to become autonomous. I think the other bit that people need to understand, and I will talk about this a bit more, is we're very much looking at this in terms of not just individual vessels or even fleets of vessels, but how this interacts with other systems which become increasingly automated, such as smart port infrastructure. Indeed, there's already a couple of projects we're looking at next year which will involve that in European waterways, and how actually autonomous barges, for example, will dock with smart ports. Another thing to emphasise here, and one reason why maritime is particularly interesting, is that it's innately international. I think it's pretty obvious to say that, but the standards are very much set at the level of IMO, but also because shipping goes from country to country, by definition, a lot of it does. It's a very international space, a very international sector, And so addressing things like autonomy, you have to look at it from an international perspective, not just a UK perspective. That presents a particularly interesting and challenging use case, therefore, but also perhaps governs some of our approaches on this. As I've already said, so we've been using our experience derived from other sectors and disciplines in this, and in particular been working with Lloyd's Register, but also some other key parties down in Plymouth in the southwest, as well as some of the other national agencies such as Met Office, to look at what is required to assure maritime autonomous systems. And that what we're looking at is to develop something we call an assurance framework for maritime autonomy, and we're looking at to become a benchmark for international adoption. Now, we call this the Maritime Autonomy Assurance Testbed, or MAT for short. And the objective in this is very much to enable the fast adoption of technology, making autonomy an affordable and a viable business, and also resulting in accelerated increased opportunities for businesses, as well as realising the benefits for the UK. So, if you like, rather than looking at it, getting a few vessels out there, it's very much how do we get these things deployed at scale, and what's that going to take? So what you see here is a very top-level distillation of the sort of core themes we have identified. And I say we, I'm collectively talking about not just ourselves, but ourselves with Lloyd's and some of the other parties involved in this. That includes partners down in Plymouth and the South Devon Free Zone, they're known as the Ocean Futures Partnership, and that includes people at the University of Plymouth, and Plymouth Marine Lab, and the Plymouth Fast Cluster, and not least Plymouth Smart Sound, which is a digitally connected 1,000 square kilometre sea space with quite unusual and very useful topography, but also very controlled space as well, which is very useful for the sort of activities we need to undertake on this. So as I said, the approach is to develop an assurance framework, and this will draw on experience from other sectors we have in transport and other applications of autonomy. It does require a wide and diverse range of disciplines. If you look here at areas such as from policy and regulatory through standards, infrastructure, data management, etc., as well as cyber safe and secure, you'll notice that this is not something, again, that a single organisation or even several organisations can do. It's very much an activity which brings in a huge range of skills and disciplines. And some of these are not very digital at all. So, for example, when we start looking at things like training, that's going to be a hugely, an area where we're sort of trying to translate where people are now in terms of their sort of knowledge in the marine space into a how you work with, how you maintain, how you develop these systems, and how you also make sure that they can interoperate with other systems. And that is going to require a wholesale rethinking on how training is done. So essentially, building on this point about what assurance is going to involve, an assurance framework, we have to look at this at three different levels. So we've got to look beyond this concept of certifying a system at a given point in time, for example, such as when it leaves the yard where it was manufactured or designed, or the factory, or even when it comes back into for a sort of wholesale ship survey once every few years. We need to look at this in terms of what is an acceptable level of assurance for these systems during operations, and what is required to achieve or confirm that. And therefore, what new test standards, systems and infrastructure need to be developed when the current ones have been designed with human operators in mind. And two examples help illustrate the diverse nature of this challenge. So first, how do you handle multiple firmware software updates to sensor systems, particularly for live and operational systems? There are examples of very large yachts with a lot of sensors on them in the Mediterranean, probably owned by some very wealthy oligarch or something, but actually just being completely shut down when one of the subsystems, which is covering the HVAC, the manufacturer of that, decided to do a firmware update while the ship was at sea. which closed down all the ventilation ports and therefore made the engine overheat and the whole ship shut down. So these are the type of things you want to be able to ensure don't happen to an autonomous system when there's no one on board, particularly to fix that. So that's one of the examples. Another one, which is something that's cropping up a lot at the moment, is how do you exercise reliable and consistent control of multiple separately and remotely operated vessels in a single operating environment such as a port? Now, some of these might even be coming in from another country where that remote operator is based in that country. And then you have to start thinking about does the port need to assume control at some point of that operation? How does that work? And it's also important that any framework supports developers and designers and future operators of these technologies to undertake R&D with greater confidence. And for example, through access to common test and reporting methodologies and access to consistent qualified data and reference data. An assurance by design approach, therefore, reduces risk and galvanizes investment. And again, in this flexibility is important. Different systems with different operating domains will likely require different levels of testing and scrutiny. One of our objectives is to develop the appropriate measurement infrastructure and performance metrics to ensure that this assurance is relevant, cost-effective, and reliable. So one of the underpinning approaches which links measurement with operational assurance is the development of tools to establish and communicate the true capabilities and limitations of the autonomous system to the users. So establishing the true capabilities and limitations involves three main steps. First of which is defining where a system can operate. So that's called conditions. Defining how it can operate, we call that behaviors, and then creating the evidence to prove both these claims. And that will use things like testing scenarios and also development modifications of any behavior codes. And this is both audit and test-based. Now, this forms one of the sort of core underlying principles, if you like, of the MAP program. And the delivery methods are being generated by WMG's VMB team, who we happen to also be working with on the CAV space as well. So what we've done here is when we're considering the operation assurance of maritime autonomous systems, we've started to look at how might the end-to-end process from design, testing, certification, and in-life operation come together. So this is a particularly helpful exercise when we're seeking to understand how the operation of autonomous systems deployed at scale and in many different shapes and sizes can be managed. And so what you see here is our first iteration of thinking on this point. So this is very much a piece of work from Lloyds and ourselves, but it's very much a work in progress and will evolve as the MAP program gets underway. And so if you remember, what we're trying to understand is firstly, on the right here, where that green star is, we've got a single system or perhaps a multiple fuse system on a vessel, or a complete unmanned or remotely operated vessel, or even fleet of vessels, and potentially even up to a smart port. And with each example, of course, there's a different degree of risk and impact, and this will influence the level of activity and scrutiny. So the picture we're aiming for is, I'll go back to where that, that first green one is. It seems to have a life of its own at the moment. So the picture we're aiming for is one of current and predicted system performance. And is it operating as expected, or is the system operating outside its performance envelope? Does this indicate a problem that needs to be fixed? And from this, we can start to determine potential future scenarios where its performance could be affected or degraded, and what risk does this mean? So here, a consistent and well-characterized evidence base, which comes through the work of the MAP assurance framework, can be referenced, and this can be referenced against equally and hopefully well-characterized operational data, which we capture where appropriate from the system or the vessel. And we can start to see why a system made the decisions it did. And at the same time, a system model can be generated via the assurance platform, against which, for example, updates to hardware and software can be tested back in the assurance testing framework. And therefore, they can be certified as safe to install or update before updating the actual system. And then combined with other operational and environmental data, this could then be used to update the risk quantification of a system's performance and an advisory to operators and or insurers of systems. Now, these in turn can, when necessary, implement changes to the operation of the system, perhaps take a different course, operate differently, etc. or potentially even, hopefully not, but come back to base to be fixed. But this can also go both ways. So potentially it could be a positive change where evidence enables systems performance boundaries to be extended. So this assurance as a service model is made possible through the development of common standards, specifications, and data quality frameworks. And these are a core output from the assurance framework. And what's it going to take to build such a framework? So this, again, is a work in progress, and it's based on what we've seen evidenced in the development of other connected and autonomous mobility as well, where trying to copy the things that have gone well and improve on the things that have perhaps gone less well in some instances, but also to give us an opportunity to accelerate some of this activity through those learnings as well. I'd like to point out that getting this framework established will involve a high degree of complex activity. I think that's probably self-evident, but the intention is that this process of assurance at the other end for developers, service providers, operators, etc., is easy to use and understand. So, as I said, don't assume what you see here is a fully accurate picture of how the program will evolve. It will become much more precise and much more specific as we move forward in terms of requirements gathering and other activities. At the cornerstone of this is a sort of creation of a ground truth and well-characterized evidence base. And this is something in discussion with the regulatory bodies, they said is very important to them, because at the moment they don't have sufficient quality of evidence and data on which to make decisions on how to regulate. So this is a cornerstone of what we're trying to do here. And so the program does follow these steps of gathering data, analysis, development of tools and specifications for testing and infrastructure, which in turn enables the actual testing and operational deployment of systems. And this is a continuous cycle, if you like, of data gathering and analysis, and it evolves as more data is gathered from a wider set of sources and scenarios. And that's, again, why we are based in this physical space where we have a degree of control of the environment and a degree of control of having gathered data. But it won't stop there. It will, we will then distribute this data gathering exercise around other parts of the UK and other parts of the world as we learn how to do this both effectively and also cost effectively as well. And as with all aspects of data, it's essential to provide a quantified and traceable approach. In this, it's worth highlighting how the activities in the physical space play an important role. And as I said, in enabling the creation of the tools and methodologies essential for the proper functioning of the assurance framework. So things like reference data for sensors to support compliance activities and providing reliable environmental and sensor models for virtual testing is going to be very important there. But other factors will be looking at things like human factors analysis. So some of our partners down in Plymouth in the Southwest have a lot of expertise in that. As do some of the other partners in development of training, but also the development of things like training data libraries, also for all the scenarios and the operating conditions and behaviours, and also supporting the development of digital colregs. And also another key component of this is understanding what are the optimal and acceptable infrastructure specifications to be deployed to ensure the safe and cost-effective operations. A good example of that is remote operations centres, which are going to be a big feature of maritime autonomy. And so ultimately our intention is to establish a distributed capability, ensuring innovation can be supported, and this is going to be out throughout the UK, but also because other parts of the UK and potentially hopefully further afield aren't all going to be coming to one place to do all their testing. That's the whole point. We want people to be able to access reference data, to be able to take their own sort of virtual testing and to build their systems where they are, but using this assurance framework to underpin that and building greater assurance in what they're doing. So I just wanted to build a little bit on the reference data for sensors I mentioned, because this is an area that MPL is particularly involved in. And so this work is really being used to support compliance activities and provide reliable environmental and sensor models, for virtual testing. And it's one of the areas where MPL, as I said, is focused and is migrating current learnings from the CAV sector, where we've been collaborating with the Met Office on this. Our approach on sensor assurance includes a series of link tests and characterization exercises at different levels of complexity, where these sensors and full systems are tested both physically and in the virtual environment. This will achieve the required level of competence and sensor performance through this test ecosystem. And this would be adopted as a feature of MAS and actually connected autonomous mobility more generally in terms of safety assurance. And it should be noted in this context, reality may include testing both the natural environment and controlled environments where weather conditions are recreated. Now, for maritime, recreating a controlled environment is probably more challenging, but there are ways of doing that in terms of scaled test beds as well. Now, the principle here is that competence in sensor and sensor system performance is built up by doing a large number of simple tests under controlled conditions. And as the complexity of the tests increases, the number of tests required decreases because the lower level tests have given confidence in system performance. The information derived from the combination and linking of tests is vital for reliable virtual testing also of the autonomous systems. And as we've been describing earlier, virtual testing is going to be an important component because it enables you to test those edge scenarios, but also test a much larger number of scenarios much more quickly than taking physical systems out where there might be a higher risk of damage or even potentially for human safety, in particularly when you've got more congested sea space tests that you want to undertake. Such tests can highlight the gaps in performance that may need to be covered by complementary sensor technologies also. And this is another important factor. This will help to identify conditions under which the complementarity of the sensors means the system as a whole is still safe even when the performance of one sensor is degraded. And this is another important component of understanding the reliability of and the trustworthiness of an autonomous system. And two other considerations I'd like to mention on this approach. Firstly, are that the individual elements of the test environment ecosystem must include linkages and ensure that the characterization information from the different tests can be traced back to national standards combined with a well-defined uncertainty framework. This is really vital for this assurance. And also determining the threshold weather conditions where sensor performance becomes degraded with well-characterized uncertainty is critical to ensure informed safety. It also enables decisions to be made about the balance of investment across the test ecosystem, potentially identifies areas of future focus of development of improved sensors. I think this is my final slide. So another aspect to the assurance framework, I alluded to this earlier, and this is a critical one, is that this is not about a single pass-fail approach to assurance. Rather, it's designed around at the earliest stages, de-risking the R&D process and is integrated where appropriate across all TRLs. This means that appropriate test methods and properly qualified data should be available even at the very early stage of research to reduce the downstream risk of system error or failure. And this also works the other way in providing a platform to inform and influence the evolution of the framework. And it's envisioned this approach will be a major driver for investment in the sector in the UK. So I'd like to finish off there and just say, really, it's just a snapshot of what we're setting out to do. The plans will continue to evolve, and there is a lot more detail behind this. Thank you for your time today, and I hope I'll be able to answer any questions you have on this.
Okay, so thanks, Andre. We should all give you a virtual round of applause, I guess. Yeah, here we go. Thanks very much for an interesting talk. And now it's time for questions. I mean, I've got some, but I'll ask them if you don't ask them, audience. Yeah, so do we have any questions from the audience? Maybe people are thinking a little bit about it before they come back. You can either slam it into the chat or ask on an open mic, whichever you prefer. Ram.
Hi, Andre. Thanks for a great talk. I missed the introductory section because I was elsewhere, but I did manage to catch up. So looking at some of the slides you're describing about, how the whole system is put together, what's the scale of the test bed? Are we talking about, a single vehicle, a network of vehicles, a harbor? What are we looking at?
So the challenge of calling something a test bed is it will never encompass everything. Plymouth has advantages that it has a lot of infrastructure there. and the MAP program will put more infrastructure in there. And there is the ability to test things like automated docking as well. However, there are other larger scale locations, not just in the UK, even internationally, although I can't mention who they are yet, we could collaborate with. The point is to use the framework as the means for collaboration, as to allow every different location in the country to go off developing its own thing. We are trying to make this something which is inclusive and engaged with other parties on this. So the scale of testbed, it is large. A lot of it, I mean, for example, one of the questions we're looking at is what range are we needing to test sensors? Is it out to 10 nautical miles? Can we do it over 1 and extrapolate out? These are questions that need to be answered. In fact, over the next few months, we're going to be doing some initial research into that area. And which bits matter. But there are definitely things we'll be looking at are remote operations into, for example, that physical space from other locations and how that's managed. That's a particularly thorny issue internationally right now. So that's one of those things. And one of the big issues there is how are you managing the situational awareness for the remote operator and for the system, and potentially for the location, so the recipient port as well. And how is that being managed, and how is that being properly characterized?
If I may
okay. Sorry, I only go around.
Would the focus of regulatory statements be at the level of kind of, ensuring automated docking and things like that, or would it be at the level of the communication protocols? So that's kind of what I was trying to get at with.
Yes. Okay. So I don't think we have all the answers yet for that, but I certainly don't have all the answers for that yet. At the regulatory level, I would observe that they tend to work at quite a high level, and then say, right, come up and with your evidence to prove that it's safe and compliant, etc. The challenge being is that no one has designed the sufficient set of tests, etc. And compliance audits to demonstrate an autonomous system fits the bill. Because in the past, you've had your vessel and you've had your marine classification societies have gone off and said, here's the vessel, it's fine, it fits the bill. Oh, and here's someone else is going and testing the sailors and the captains, etc. and saying, yes, they're qualified and they're fit to do this. And I think recent stories have shown that that's actually quite a big issue. That actually, sailors are trained in a number of different levels. They have their core job, but they will have other jobs to fulfill and other training as well for being at sea. And these are all things that need to be factored into how do you operate something that's autonomous. Now, again, it's not just about vessels that pilot themselves. Many of these vessels will still have humans, but they may have handed over some decision making to a system that makes decisions on their behalf. And really, it's looking about this across the spectrum, but also looking at it at scale and where do those challenges emerge. And the scale issue is the thing that particularly is a particular challenge, and why assurance is something that we need to have a control over. When I say control, we need to know what we're doing. If we just start buying systems from another country without really knowing how to prove their reliability, prove their safety, prove their effectiveness, if you like, there is a failure that we don't understand across that system. How do we begin to remedy that?
Okay, so next we have Sian. Yeah, I think you have to unmute probably first.
I do. I'll definitely unmute. Thanks, Andre. I mean, look, I had a question that kind of touches on that, and it's this. First of all, who are the regulators that matter here, in the UK context specifically? But I guess for those of us who don't know a lot about maritime issues, the kind of international element of this is fascinating. So how does the UK play with non-UK? And the second part, this is the second part of that question, you've touched on it a little bit, is what are the issues that matter for these regulators when you're talking to them? And arguably on our roads, it's safety, right? When it comes to autonomy, is safety still the paramount issue there? Or are there other things? That's it. Thanks.
No, those are both really good questions. So and they're very intertwined. So in the maritime space, the regulators, to a very great degree, are enforcing international standards. It's a very international space. So the IMO has 180 something countries as its members, flag states, and they will all contribute to deciding what new standards are developed. And obviously, this means that something like autonomy is particularly challenging, because that might seem to threaten certain countries where, for them, seafarers are a large part of their economy, for example. So those things to be taken into account as well. That's not really the problem we're trying to address. What we're trying to focus on is how can we ensure that the UK has a role in this, partly because I think the UK could do it well. And I think the UK can be very transparent about it, but also we want the UK to have some influence on this. So the MCA, the Marine Coast Guard Authority, for some reasons the MCA, not the MCGA, is the regulator here. And then you have the naval regulators as well, who come into that. But from a civilian side, you've got the MCA. They're an arm-length body in Department for Transport. And they will interpret what's coming through from IMO, and they will regulate according and interpret that for the UK. Now, what you have then, though, is their focus is what's at sea and seaworthiness of vessels, etc. And then on top of that, things like the behaviour of seafarers, etc. One of the challenges here comes, what do you do about ports, which is responsibility of different groups. So you've suddenly got different bodies that are looking at that, and that becomes law on the land. That's a more UK-centric space as well, potentially. So you've got it's much more complex. So one of the things that we're looking at here with this is how do we ensure that, if you like, there is that sort of integration and interoperability between these different systems, which might come under different regulatory jurisdictions. And I think that's one of the challenges. On top of that, ports will have increasingly smart operations, some of which will again be handing over to some sort of automated autonomous system. And then on top of that, not to complicate it too far, is there'll be increasing use of unmanned aerial systems for surveying, etc., and potentially for other operations as well. So there's a whole range of other things that need to be considered, and we will be looking at that. I hope I helped answer that question a little bit.
Okay, do we have any other questions? If not, I'll ask one. So, Andre, I wanted to ask you a kind of hoary old chestnut, which is what do you do about security? I mean, it seems it didn't get a lot of publicity or a mention in your talk. I think you mentioned cyber once, but it does seem like this is a particularly potentially adversarial environment, because you could be sailing these ships around the Horn of Africa. And it does seem like fully autonomous ships could have significant benefits in terms of removing harms to people. But then there's a balance against something which is an extremely expensive capital item, so how do you balance those things, I guess?
I think there's several layers to the question of security. I'll slightly turn that on its head. So at this stage, we are more focused on the cybersecurity side and other aspects of assurance related to security than I'm out at sea and someone might try and board my autonomous ship. One thing I'd say is, again, I don't see the £1 billion cargo large car carriers being unmanned, but nor do I see them as currently being particularly able to defend themselves beyond the simple fact they're so large. Is actually boarding those things, I have been on them, is nigh on impossible without a very large ladder. So, I think there's some, I don't think that question is the main one. I think one of the questions we're looking at, though, is if you are a operator of a mid or large size smart port where you have a whole range of systems going out, some fully manned, some completely unmanned. Say, for example, you're operating systems that maintain and do surveying on offshore renewables and support aquaculture. At one end of your port, at the other end, you've got bringing cargo, and you've got maybe smart tugs there, which are operating on an unmanned basis, which is, we've seen in evidence, in fact, had been involved in some projects involving those. And then all these systems follow the assurance framework. Then suddenly a few systems turn up which are remotely operated but haven't been followed your assurance framework or the assurance framework. Do you put them in the naughty shipping lane and say, well, you can't come, you have to go this speed, and you've got to go to the back of the queue, and you have to come in when there's less systems around? These are all things that need to be considered. And how do you even communicate with those systems? Then you've got the next tier, which is the I wouldn't say classic, but it is the cyber security risk. So it's both cyber safe and secure in this instance that we're looking at. That is work, in this case, that's work that's going to be led through University of Plymouth, but in alliance with other organisations as well. And we'll be looking at how tools such as simulation modelling can support that as well. That is something that needs to be addressed at quite a broad level. I don't think it's something you address for one particular type of shipping, or even just potentially just for maritime. I think there are sort of broader challenges there. I think the one last thing I would say is the other aspect of security we look at is it's either done through a sort of some sort of opponent or aggressive or negative agent, or it's done by accident, but it's actually where you can modify something that a sensor might be looking at to fool it into thinking something else. I haven't come across these issues quite so obviously in the maritime space yet, but for example, you can use reflectors to make radars thinking they're looking at something much further away than they are. And certainly on imaging, you can do things which might change what a perception system thinks it's looking at, and therefore it will change its behavior.
Okay, any more questions? I'd add one more, or maybe two more, if nobody else is going to ask anything. So these are already extremely complex systems. I mean, if you look at a ship, you know, I was looking at your sensors picture, and there must be a massive number of sensors already on board most ships, you know, because there'll be something doing planned maintenance, for example, on most of the plant, yeah, and detecting all kinds of things. So what are the integration challenges that you see in terms of the introduction of autonomous components into this environment?
I think I see them as being significant, and I don't think, and I think you're absolutely right to point this out. We shouldn't underplay the importance of integration with those sensors which are telling you steering direction, etc., or other aspects of the ship performance, engine performance, etc. All these other factors. Again, to date, there have always been people on board the vessels that can monitor and indeed fix things. But if you have a vessel out to sea, or a system that's standalone on land that's doing something in an automated fashion, how do we know that those sensors are performing and in the right way and giving the right data out? And that's a huge challenge. So that's one challenge, and then integrating that again. I think one of the things that we argue for, one of the underlying principles, if you like, of the whole MAT program is for it to be independent, for it to be as far as possible open and available to everyone. So not something that's just there to create a, if you like, maybe sort of a bit of a vendor lock-in. But therein lies one of the opportunities and one of the challenges, is how do you ensure that people are developing systems that can integrate and be integrated both within individual systems themselves, but also at systems to systems level.
Okay, thanks. Well, look, we've got 5 minutes left, so I'm going to ask you my very last question now, Andre. You mentioned data gathering, yeah? Do you think are you planning to do proactive data gathering? You know, because in a sense, you want to think about what the operational risk is, yeah? And say banks, for example, have very extensive operational risk databases. Do you plan to start collecting that, to kind of have groups of shipping operators who are prepared to gather data on incidents, so that actually you have some more comprehensive catalogue of those things in terms of driving your simulators and so on? Because I guess that, say, in automated vehicles, then Waymo are doing that in a big way. by driving lots of cars around the US road system and picking up data there?
Yes, we are. I don't know, one of the challenges, we don't know what Waymo are doing with that data or how they're interpreting that data, and whether or not there are, what's the impact on that on the performance of their system. What we're looking to do is to use our data gathering activities to help both develop tools, but also build the reference data sets that people can use for developing their own system. So understanding what are the optimal types of training data, for example, for sensors of different types is one example. But data gathering will be helping us firstly with things like that sensor assurance side of things, and also being able to build reliable models for virtual testing. But it will also inform the development of scenarios. So that will be, yes, getting information from accident and other ship logs as well. We have to bear in mind that data might be limited. So there'll only be certain aspects of that data which we can use, and that data might be incomplete. It probably will be incomplete for our purposes. So we need to back that up with our own data gathering exercises. And one of the things we're looking to do, but this is still a work in progress, is also have data gathering systems fitted on vessels that are operating way outside the testbed. So they might be going around the coast or going into other countries even. But we need to understand how can we rely on that data, how do we even get that data back to us, because that in itself can be quite challenging, particularly huge volumes of data. So all those things come into play. But also how you therefore use that, as I said, to build your scenarios, to build your training data. All these aspects need to be ground truth, if you like, have a single point of truth. And this is part of what we're trying to do, is to enable people to do that. And that's also why we'll be doing it beyond Plymouth as well.
Okay, thanks. Okay, so there's an opportunity for one last question if anybody wants to ask one.
I see a couple of colleagues who stayed silent, so either they're going to beat me up afterwards or congratulate me, we'll wait and see.
Yeah. Yeah, anyway, thanks for a fascinating talk, Andre. That was great. And it certainly opened my eyes to the complexity of fully autonomous shipping. Yeah, so that was very interesting. Thank you very much. Okay, so we'll give you one more virtual round of applause, and then we'll let you off the hook. Yeah. So,
right. Anyway,
thanks very much.
Bye, everyone.
Bye now.